So, let us look at an example in geometric optics. Geometric optics. So, let me say that I am given a variable, I am given a coordinate system x of y, x, y, z, where z now is the independent variable, and my z lies in the interval which is a subset of R. It describes, z describes a curve, z describes a curve gamma, right. Then my optical path of length, gamma in a medium, with refractive index. So, I am going to with a refractive index n of x comma y comma z is, so the optical path is given by the extremal jy of the integral from x0 to x1 of n of x y z times the arc length integral x prime square plus y prime square dz. Okay. So, to make sure that the curve described by gamma is the optical path length, or the path length which is the shortest path length travelled by the particle of light, the answer to this is given by extremizing this path length or the arc length integral. Okay. So, we can directly apply our formats principle. Again, I am following our example done in lecture 3. We have used a simpler version of extremizing this, a simpler integral where n was taken to be 1. So, by formats principle, I see that the necessary condition for gamma to be light ray is that J is stationary or J has an extremum. J is stationary or J has an extremum. So let me, in order to find the extremal of this functional, let me introduce new sets of variables. So, my new variable q1 is x, my new variable q2 is y, and my new variable z, my new variable t is equal to z, which is the independent variable, right. So, now I have the length of the interval from z0 to z1 is changed to t0 to t1, right. And then further note that my Lagrangian L of t comma q bar dot is given by n of t comma q bar. Well, this is this quantity transformed in the new variable times square root of 1 plus q bar dot square, right. Okay. So, this is the so called optical Lagrangian. Okay. Well, let me call this as the optical Lagrangian right away. Okay. So, then the next step to solve this and find the extremal is to introduce our conjugate variables p and h. So, I introduce our variable p. So, pk is partial L partial qk dot, and by the definition of L, this comes out to be n times qk dot, just plug in the expression for L, and I see that this is partial. So n by n qk dot divided by 1 plus mod q bar dot square, right. So and also from here I can see, note that I have the relation that p1 square plus p2 square minus n square, it comes right away from this expression for pk, is equal to minus n square by 1 plus mod q bar dot square, right. Okay. Or my function qk dot, qk dot can be derived from this relation. My qk dot is pk by n times square root of 1 plus q bar dot square, right. Okay. And this is, well, I can always from here I can see that 1 plus mod q bar dot square is n square divided by n square minus p1 square minus p2 square. So from here I see that this is also equal to pk by n times square root of n square by n square minus p1 square minus p2 square. I see that this is also equal to pk by square root of n square minus p1 square minus p2 square. Okay. So then my Hamiltonian h, the other new variable is defined as follows: h of t comma q bar comma p bar in terms of these variables is by definition summation of qk dot pk, k from 1 to n, minus L, right. And after plugging in all the values, I have already defined qk in terms of pk. I see that this is also equal to summation pk by square root n square minus p1 square minus p2 square, and k is from 1 to 2 times pk minus L. Now L is n square by square root n square minus p1 square minus p2 square. Okay. And then after substitution I get, after simplification I get that this is also equal to n square minus p1 square minus p2 square, and that is my Hamiltonian. So the moment I have defined my conjugate variables described by this checked relation, I can immediately write the Hamilton's equation. The Hamilton's equations are as follows. I see that qk dot is partial h partial pk, the first relation, and we can directly plug in the expression for h. We get that this is also equal to pk by square root n square minus p1 square minus p2 square. Okay. So this is a 2D problem here, 2 dependent variable problem, and my variable pk dot is equal to minus del h del q k, del h del q k, which is after substituting we get the following relation: n square minus p1 square minus p2 square times del n del q k. Okay. So from here all we need to do is to find out, to solve this system of equation, and that can only be done once we have an exact relation for n. We don't know what is this function n. So I leave this question at this point, assuming that the Hamilton's equation is solvable, right. So these are my Hamilton's equation. So at this stage we know that once we are in the Hamiltonian formulation, we should be very easily be able to solve our Euler. We should be very easily be able to solve to get our extremals via the Hamilton's equation, right. So this question is that true? given a Hamiltonian system, can we really solve all the time, can we really solve the Hamilton's equation? The answer is not really. It depends how complicated this function h is, right? If so, the question is, suppose h is quite complex that we are not able to solve the system of Hamilton's equations, then can we reduce that system or reduce that Hamiltonian to a simpler case or a simpler Hamiltonian? The answer is yes. And to reduce from a more complex to a simpler Hamiltonian, we use a transformation or a map known as the symplectic maps. Okay. So, what are symplectic maps? Symplectic maps. Okay. Let me denote it by SM. So, SM is a transformation. So, SM is a transformation, right? SM is a transformation from the phase space. SM is a transformation from the phase space q bar comma p bar to the phase space to a new phase space q bar comma capital Q bar comma capital P bar, and of course there will be the Hamiltonian in this space is h and the Hamiltonian in this space is h hat, not necessarily identically or functionally equivalent, but the idea is we are reducing a Hamiltonian which is far more complicated to a Hamiltonian which is simpler. So, let SM be the transformation from one phase space to the other, defined by the following relation. So, QK is QK of T comma Q bar comma P, and PK is PK of T comma Q bar comma P, right. So, this is my map such that well, I need to define certain relations. Let us go back a few slides. Where is my Hamiltonian mechanism? Well, Hamilton's equation here. So, my this set of equations or the Hamilton's equations are denoted by 2. So, we are going to use this numbering 2. So, in this result it says that such that the Hamiltonian the Hamilton's equation 2 or I would say the Hamiltonian system such that the Hamiltonian system given by the Hamilton's equation 2 transforms into another Hamiltonian system, right, where I am given that QK dot is equal to del transformed into another Hamiltonian system H hat, right. The older Hamiltonian system was H, the new Hamiltonian system is H hat, such that the Hamilton's equation is still preserved. So, QK dot is del H hat del capital PK and PK dot is minus del H hat del capital QK, right, QK. So, my Hamilton's equation are still preserved, right. So, here note that my H, the original Hamiltonian system was a function of the variable small q small p, and my new Hamiltonian system is a function of capital Q and capital P, right. Okay. So, note that symplectic maps, so that is the definition of my symplectic maps. Note that symplectic maps are also known as canonical transformations. Okay, symplectic maps are also canonical transformation, a map which changes the coordinate system but preserves the Hamilton equation. Okay, what are canonical maps? A map which this is in layman's term, which changes the coordinate system but preserves the Hamilton's equation, right? Hamilton's equation in the new system is also is still satisfied. Okay. So which means that the corresponding extremals, well, the corresponding functionals in the T comma Q comma P framework are given by J of Q bar, which is integral from T0 to T1 L of T comma Q bar dot dt, and the corresponding functional in T comma capital Q comma capital P bar is of the form J of capital Q bar, which is integral T0 to T1 L of T comma Q bar comma P bar dt. Okay. Okay. Right. Well, if we have Q dot here, so this will be Q dot here with a capital. Okay. Such that my Lagrangian of T comma Q dot is of the form summation Pk Qk dot k from 1 to n minus h of T comma P bar comma Q bar, and my Lagrangian in the new coordinate system is summation Pk Qk dot k from 1 to n minus h of T comma P comma Q. Okay. So which means we introduce a new term known as the variationally equivalent. We say that J, so let me call this function as J hat to differentiate it from J. So J and J hat are called as variationally equivalent. So they are variationally equivalent functionals. They are variationally equivalent if they produce the same extremals. If they produce the same extremals. Okay. If they produce the same extremals. Okay. From here, okay. So the symplectic map is the map which changes the functional J to functional J hat, that is via changing the coordinate system, right. So it's a the symplectic maps are quite important in our investigation of finding the Hamiltonian system. Why? Because symplectic maps is a transformation from one set of extremals to another, right. So we definitely in our description of our Hamiltonian system, finding symplectic maps is critical. It's a transformation from one set of extremals to another. Okay, to another. Okay. Now this question is, well, having seen the importance, this question is how are we going to find the symplectic maps? One way of finding the symplectic maps involves the introduction of the so called generating function, right, and we will see what are those. So one method of finding symplectic maps involves introduction of a generating function. Right. It is the generating function. Through the generating function later on we will describe the famous Hamilton-Jacobi equation. So let us see what we have just said. Okay. So, I want to elaborate on this statement further. Okay. So, suppose I am given a smooth function phi. There exists a smooth function phi such that summation pk qk dot minus h of t comma q bar comma p bar. So, what is this? What is this sum? This is the Lagrangian, right? So, this is the Lagrangian. So, the Lagrangian in one frame is equal to the Lagrangian in the other frame, right, plus the derivative of phi with respect to t comma p comma q bar, the derivative of phi with respect to t. So, assuming so suppose such a phi exists, right. So, this is my Lagrangian L hat. So, assuming j and j hat are variationally equivalent. So, assuming that one set of extremals could be converted to the other set via the symplectic map. So, suppose j and j hat are the functionals corresponding to these Lagrangians are variationally equivalent, right, and the map given by qk, which is qk or q bar, which is q bar of t comma q bar comma p bar, and p bar is capital P bar of the old variables or variable in the older coordinate frame, is symplectic. Suppose this map is symplectic, is a symplectic map SM. Okay. So, then which means the moment this map is symplectic, it implies that we can convert my function phi from one set of coordinate frame to the other set, right. We can convert this from one to the other. So, phi is the same phi. So, q bar comma capital Q bar. So, we have just replaced one conjugate variable p with capital Q. Okay. So, then let us rewrite, let me call this as this equation as star. So, we rewrite our equation star, in the generalized coordinate or in the new coordinate frame. Rewrite star in the generalized coordinate frame, we see that this is also equal to d phi dt. Phi now is a function of small q comma capital Q, right, because of the symplectic map, minus pk qk dot minus capital Pk capital Qk dot k from 1 to n plus h hat. So, I have just rearranged all the terms here, plus h hat p comma q minus h of t comma p comma q, right. So, let me call this relation as A, right. Now we rewrite this left hand side again. So, using chain rule, I see that d phi dt is also equal to summation k from 1 to n. It is del phi del qk times qk dot. Note that phi is a function of q and capital Q as well, right, plus del phi del capital Qk times capital Qk dot, right, and this is all under summation, plus del phi partial t. So the total derivative of phi is the sum of these partial derivatives. Now let me call this relation as B. So now I am going to compare. So what I am trying to do is I am trying to find an appropriate equation for this generating function phi, right. So this is all capital Phi. Okay. So comparing A and B, I see that note that the coefficient of Qk dot is Pk. I see that Pk is partial phi partial Qk, and capital Pk is partial phi partial Qk, right. I call this relation as C, and well, we have a minus sign also, so this will have a minus sign. And finally, so note that this C, so C gives the relation describing the generating function, describing the generating function, through which we find out the generating function, and that leads to our symplectic map. We will see through an example. And then we use C, using C and A. So once we have compared everything, all that it remains is that the partial phi partial t is the sum of this Hamiltonian. So using C and A, all I am left with is that h hat of t comma q comma p bar is equal to h of t comma p, well, t comma q bar comma p bar plus partial phi partial t, right. So this is the relation. Let me just take back few words. So the first set of relations, C, is the relation describing the symplectic map, and this relation describes the generating function, phi. Okay. So we are ready to look at the power of symplectic maps through some examples. Okay. So the example I have is the following. So the example is that of the harmonic oscillator. Right. Let me call this as HO. So the Hamiltonian for the linear harmonic oscillator is H given to be the sum of the kinetic energy plus the potential energy, and I write it in terms of the conjugate variable P and Q. So the Hamiltonian is given by 1 by 2m times P square plus omega square Q square, right, where we see that Q is the position, and P is, well, the constants, the variable Q is the position, m is the mass, and T is the time of integration, which we will see soon. So these are my variables. My P is the momentum, and what else? My W, well, in Newtonian mechanics, W denotes a physical quantity known as the angular velocity. Here we will denote W to be a constant without going much into detail. So it's a constant, right? Okay. So which means my Hamilton's equation, the moment we have a Hamiltonian, my Hamilton's equation are as follows. Equations are Q dot is equal to partial H partial P, right. So which I can find that this is also equal to P by M, right, and my P dot is minus partial H partial Q, which is also equal to minus omega square q by m. Okay. So that's my Hamilton's equation, and the rest. So we need to find to describe this Hamilton's equation in another Hamiltonian, we need the symplectic map and so on and so forth, right. So well, symplectic map, and then we need the so called generating function, right. Later on we will see that the finding generating function is very methodical. Right now, using some hit and trial, we assume a form of generating function, and the form is chosen so that the Hamiltonian in the new coordinate frames is very simple. Okay. So let us so we choose our generating function phi of q comma capital Q to be omega q square by 2 cot q, right. So this is my generating function that we have chosen. Again, right now the choice seems very arbitrary. In the next topic of discussion, we will see that the choice is not random but follows a very specific set of equations, okay, or the Hamilton-Jacobi equation. So let us assume the generating function of this form, right. So from here I can describe my variables. Note that the moment I have the generating function, I can describe using this C, condition C, I can describe my momenta variables Pk and capital Pk, right. So the generalized, well, the momenta coordinates are P, which is equal to partial phi partial q, and my capital P is minus partial phi partial capital Q, right. And from the above I get that partial phi partial q is omega q cot capital Q via this relation that we have assumed, and from the second one I get that this is also equal to omega q square by 2 sine square q, or 1 by sine square q or cosecant square q. Okay. So we can also invert to find the relation between small q and capital Q, to see that my small q, so in the original coordinate frame, the coordinates q and p can be written in terms of capital Q and capital P. So this turns out to be 2p by omega times sine capital Q, and small p turns out to be 2p omega cos capital Q, right. This can be readily checked from this relation, and so these are my symplectic maps, right. So these are, let me call this as star and this relation as double star. So star and double star are my symplectic maps in one coordinate or the other, right. So which means now I am ready to describe my Hamiltonian in the new coordinate frame. So the Hamiltonian of p comma q in the new frame is, well, 1 by 2m. It is the Hamiltonian in the original frame, p square plus omega square q square, right. So I can readily substitute in this frame. We see that this is also equal to 1 by 2m times I plug p square, which is square root 2p omega cos q times to the power whole square plus omega square q square, which I get to be omega square root of 2p by omega sine q, right. This is whole square. I see that this is h hat. Okay. So once we simplify this expression, I see that this is also equal to omega by m times capital P. So notice now the Hamiltonian in this new frame capital P capital Q is relatively simple compared to the Hamiltonian in the original frame small p small q, right. So if I were to, so which means my Hamilton's equation in this frame, let me denote it by the associated Hamilton's equation. Hamilton's equation in this new frame capital P capital Q is, let me call this capital Q dot, capital P dot is del H hat del P, and this is del minus del H hat del Q. From here I get that this is omega by m by the relation that I have just found, and this, since H is independent, H hat is independent of Q, I get that this is equal to 0. From here I can quickly solve for capital Q, which is omega by m times t plus a constant of integration C1, and capital P is the constant of integration C2. Note that now I have found the solution to the Euler-Lagrange in a frame capital Q capital P. So all I do is we plug this variables into our expression double star to find small q and small p, and we get that small q after plugging in all the expression is 2c2 by omega sine omega t by m plus c1, and p is square root 2c2 omega cos omega by m t plus c1, right. So these are my variables in the original frame, and these are my solution to the Euler-Lagrange equation. So this exercise in this example has shown how can we use the power of Hamilton's equation, symplectic maps and generating function to quickly arrive at the extremals, which would have been very difficult to solve had we used the Euler-Lagrange approach. Okay.